So we'll have Eloisa Bentivengna, which will talk about relativistic simulations of large-scale structures.
All right, thanks very much. It's great to be here today to present this work, and I have to thank the organizers for the invitation. Cosmology is a relatively new area for me. I knew many of you through your works, but I really only met you yesterday. And that's really quite nice. It's definitely one of the term. Now, when I do go to cosmology conferences, I always notice that people tend to get very excited about simulations, perhaps too much. And so in order to sort of start this talk with a disclaimer, I would put up that line that describes this sentiment very well. I like to, you know what I'm talking about. Nobody trusts the model except who wrote it, and everybody trusts the measurement except who made it. And you could just relate the simulation where that's pretty much a measurement. And that it is true. I mean, take it from a numerical relativity. Simulations are great as tools for probing individual circumstances, individual configurations, but they're not theorems. They don't have the same cultural standing for the theoretical work. They need theoretical, they don't stand around. They need a framework in order to be made sense of, in order to be interpreted and to sort of build, if you want, a scientific set of scientific principles. And so it's really nice that along with the simulation, several of you are working at precisely to build this theoretical framework. And I very much encourage that work because it has helped a lot frame this these results that I'm going to be talking about. And you will see some connections between my talk and certainly the talk of Tens yesterday and the talk of other people at this conference. And this synergy is extremely important. And I also have to thank my collaborator, because he's also been integral in building exactly this understanding that has to underlie the simulations, otherwise it's basically not science. Now, with this disclaimer behind us, I'd like to move on to basically this picture. This is exactly the system that I'm going to be talking about today, the system that I do simulations about. Of course, this itself is a simulation, but let me take it as a representative picture of the system that I'm talking about. You could argue that this is the largest system that physical theory has been built, or physical theory that's testable has been built on. We already know that by confronting the observations with the theory that we have about the system, things are not quite so. I mean, there's a very simple theory that in principle can explain very many observations, but things are not so simple as one would like. And in principle, one knows that there's something about how the system gravitates that is a signal either of new physics or something that we fundamentally don't understand. And of course, try to build more sophisticated picture of the system is extremely difficult. First, because it is a compact system, so people who work in gravitational ways usually tend to think of compact system as something with a very high density, whereas that's not necessary for a compact system. Compactness parameter can be very high for systems that are incredibly diluted as long as they're big enough. The universe is one such thing, so there will be relativistic effects that you have to take into account. The system is multi-scale. That means that you have dynamics that happens over at least 6 orders of magnitude. I mean, even if you compare with traditional numerical relativity that takes studies gravitational wave sources, in those simulations, they perhaps have to handle something like 2-3 orders of magnitude, and they already have a terrible time as it is. They have to do a lot of matter distributed in very asymmetric ways, and to include all the relativistic effects in it. And on top of that, unlike many astrophysical events, the duration over which the system evolves is comparable to the time that light take to propagate from it to us. So all of our observations are in fact convoluted with the evolution of the system. This isn't a single event that lasts maybe a couple of milliseconds and then the information is propagated as we see it as it is. There's obviously a null section, a null cross section that you have to do through the system, and that also complicates things. However, so as I said, we have a very simple framework to analyze this. This is usually called the concordance model, and you very well know it. This has also been presented by Tim yesterday. You have these 3 ingredients. You have an exact solution, which is a completely homogeneous and isotropic model for cosmological model that always add perturbations. And when you go and study the smaller scales where collapse is happening, of course, perturbations don't help you anymore. But you say, okay, I don't have to worry about relativity at that point, and I can just do Newtonian physics. So you have this sort of separation of scales between the 10 gigaparsec, if you will, the CMB scale, and the galactic scale, where you say, okay, from here up, I do relativity linear, from here down, I do Newtonian nonlinear, and I don't have to worry about the overlap. And this is usually deemed to be a good enough model, but of course, when you talk about good enough model, that could quantitatively depends on what you're going to do with the model, what you're interested in studying. If you're interested in comparing with observation, that scale is set by the precision of the data sets you try to analyze. So as the precision of the data sets increases, you obviously have to step up into your model. And precision cosmologists something that's often said, it's not just a matter of getting better data, you also have to do a better effort, theoretically. And if you don't do that better effort, then you're going to get to a point where your theoretical model is going to have a systematic that's higher than your statistical error. And I would say that perhaps we're already starting to see this in cosmology, as many missions and data set report that they're seeing different, let's say, slight tensions in some of the parameters. A very famous one is the H0 one. So right now, these 2 values are reported in the literature, depending on what data you use to measure this constant. And again, the resolution of this tension is probably somewhere in the systematics. Exactly what is going to be required in order to resolve this, it's frankly unknown. And perhaps this is one of the early signs that we need better models. And then again, perhaps relativity is going to play a role here as well. So basically the idea is that, okay, when we had this sort of cosmology, perhaps the concordance model was great, but now we step to this, in fact this, as of a few years ago. And this means that we need to be doing exactly the same sort of transition at the theoretical level. All right. And this is particularly important, in fact, not just in cosmology. That's not only a question that's an end in itself. You have to remember that in many in general, many astrophysical studies, a cosmology is a fundamental ingredient to interpret other things. So if you get your cosmology wrong, you're also going to get other things. This error is going to propagate into other data. And a good example is the one that came out at the beginning, sort of early this year, the paper about the first gravitational wave detection, where they basically try to, they have to measure the masses of the component of the binary that coalesces and emits the gravitational wave. They have a measure of the luminosity distance from the source, which they can measure. But then, in order to get the masses in the rest frame, they need a measure of the redshift. And in order to get a measure of the redshift, they need a cosmology. in order to go from the luminosity distance to direction, they have to assume a model. And they assumed, of course, a lambda CDM. But as you see, they took H0 as one of the, if you remember that table, on the very low range of the measurement of H0 that are accepted today. If they were to take this, so this is almost 10% higher. Correspondingly, their estimate of their masses would change by 10%. Instead of having, was it 29 and 36, so they would have something higher than that. And maybe for black holes, this isn't very important, but imagine that this was a binary neutron star. So people studying neutron star are very serious about the mass of the star because that tells a lot of things about, say, equations of state. And an error bar of 10% is huge. So it is important to do cosmology, not just for cosmology, but also for everything else. Cosmology tends to be sort of the tier 0 upon which many other things are constructed. Okay, so now people, of course, are very aware of this, and there's been many studies lately that have addressed exactly this. How do we try and make a better model for cosmology? Perhaps something that starts to factor in relativistic homogeneities into the picture. And so the kind of workhorse of nonlinear structure formation are embodied simulations. So it's only natural that people started looking into inserting relativistic effects into the embodied simulations. And this has been done in various ways. There was a paper by Daniel Thomas and his collaborators in 2014, I think perhaps even 2015, where we took a look at a specific aspect of embodied simulations and the relativistic effect they neglect, in particular frame dragging. And then Julian Adamek has been working a lot on this, and there's now an evolution code, in fact, that you can use where relativistic effects are included at the linear level. However, sometimes when you present things as a perturbation of Newtonian gravity, you miss a lot of things because relativity is not just a quantitative change in Newtonian gravity. There's many qualitative aspects that are different. And so these sort of post-Newtonian or post-Friedmanian approaches may miss some important features. First of all, we have this thing that I think we use automatically when we analyze a homogeneous or any cosmological model, but it really only strictly applies to homogeneous and isotropic models. There's a nice correspondence between the value of the curvature, the value of the density parameter. In a sense, when you try to fit this model, there's a very precise logic. There's only really one aspect, one parameter that describes this model. So once you change that, everything else follows. In homogeneous cosmology, you lose this nice correspondence. In addition to this, when you have a homogeneous and isotropic space, it's very easy to describe what you call cosmological observers or moving observers. When you have an inhomogeneous space, and this is strictly speaking impossible, because you really only have one gravitational field. You cannot split it into a global one and a local one. That's always going to be an arbitrary process. And that makes things more difficult because you never really know whether something that you're observing is what cosmologists call a local effect, or whether it's something that is due to the cosmology. Similarly, optical properties change dramatically in some cases. That nice idea that you have a time homogeneity in a cosmological model is actually very strictly tied to the presence of a spatial homogeneity, and so if you lose one, you lose the other. This was a very nice paper last year that explained this. So there's special times that happens in certain cosmological models where things happen that don't happen in other times. Inhomogeneity in turn, this is the back reaction problem, can affect the expansion. In fact, they will affect. The question about this is what the extent of this connected with back reaction is, but there will be one. And finally, if you then let this go beyond the perturbation regime, such as in collapsing errors, and many people have been analyzing this lately, in particular in scalar field cosmologies, then also things change by a lot. So if you're structure formation studies are based on Newtonian physics, you may be missing some elements. And also, of course, if you want to build averages, averages in relativity are difficult because you can only really average Einstein, the scalar part of Einstein's equation, the vector and tensor part you don't know how to do, and therefore, if you want to go ahead with a sort of analytical formalism, then you have to, in a sense, make some assumptions. That's the core of the Booker's formalism. You can get up to a point, and then you have to make up equations that close the system. So the good thing is that, in principle, there are methods. People have been thinking about it only just now. There's several decades of research in how you integrate Einstein's equation exactly in 3+1 dimensions. And so you could take some of the methods from there. The idea is what's called the 3+1 decomposition. So you have a space-time. You identify a scalar function on it that has equipotential surfaces that are always space-like, so in a time-like normal, which is this. And then you can project Einstein's equation parallel and perpendicular to this vector. Or in fact, you have a little bit of a degree of freedom. You could vary your time coordinate in a certain way, as long as, of course, this vector remains time-like. And this is useful for certain applications. But in any case, the deal is that you would have a line element that looks like this. You can introduce an auxiliary variable which represents the first time derivative of the metric in order to decompose your second order system into a first order system. And then Einstein's equations become these. So we have two equations, one a scalar equation and a vector equation, which do not contain any time derivatives. These are called the constraints, the Hamiltonian, the momentum constraints. So these are equations that your gravitational field has to satisfy at all times. This is similar to the fact that for electromagnetism, the magnetic field has to be divergent frequency. In order to have a physical gravitational field, you have to have these two conditions satisfied. And then you have a set of equations for gamma ej is the spatial metric. This is its first derivative, so this replaces the second derivative of the metric if you want. And these are the things that you use for evolutions. You set initial data, and then you integrate this. It's basically a huge system of PDEs. It's a bit complicated, but it's nothing conceptually new. People know how to integrate these things. You can use standard numerical analysis methods in order to get a solution. And this, of course, like I said, there's several decades of work in this section, in this area. And mostly it has been applied to gravitational wave sources, because in that case, of course, you really have to, no other approach that you can use in order to get the central part, the highest intensity part of the gravitational waves, the parts where two objects merge, can only be worked out in full numerical relativity. And so this has been applied to many things. Now there's this picture which has become kind of iconic in gravitational waves. Every time you ever talk about gravitational waves, you kind of have to show this one. And the good consequence, the good fact about the existence of this field is there's also codes that you can get in order to, of course, in order to integrate Einstein's equation in 3+1 to build any exact, or I should say, as close to exact as you want, space-time. And this, as a matter of fact, has also been done in various circumstances. In numerical relativity for cosmology is certainly a minor part of numerical relativity, but it's not new. There's a Levin-Review relativity that kind of gives you the history of the works that have been done in this area. And I particularly like this review. So this is Numerical Cosmologies by John Centrella, 1981. And the thing that I like about this review, so she talks about what has happened basically in numerical cosmology using sort of cosmology using numerical relativity. And she sets up her presentation, her review, based on the discussion of what she calls misconception 1 and misconception 2. Misconception 1 is that general relativity is not important in astrophysics. And misconception number 2 is that general relativity is intractable. And I like this because So the conditions, of course, have changed a lot since 1981. First of all, there was no dark energy in 1981. There was a completely different picture of the universe. And there certainly was a completely different access to computing resources. And in general, the available computing power was at a completely level probably unimaginable today. I remind you, 1981 is the year where allegedly Bill Gates said that 640K ought to be enough for everybody. It nice having said that, but that's irrelevant. 1981 was a time where 640Ks of memory was considered a huge amount. And notwithstanding this huge change, these two misconceptions linger in the field. So we're still, in a sense, working to provide arguments why both of these things are, in fact, not quite exact. And that will also kind of cast my presentation in terms of these two misconceptions. I'll discuss mostly misconception one, because that's really the relevant one. If really general relativity is not important, then we don't need to bother about it. Right? But I will also give a couple of slides at the end about the tractability. How much can we really do with full numerical integration of Einstein's equation in a cosmological setting? So in order to start this, first I will start talking about what has been done. So there's quite a bit of history. Numerical relativists are very aware of the studies of the approaches to singularities in cosmology, mostly pioneered by Bentivengna. There's essentially at least a couple of studies per decade on homogeneous cosmology. Some in the 80s, some in the 90s, some in the 2000s, some that came out last year, a few years ago as well. This is a sort of standard inhomogeneous cosmology, inhomogeneous inflation studies. You start with a scale field that's distributed inhomogeneously, we follow the evolution, see what changes with respect to the normal setup. Another area of great interest is the one where you study still gravitational wave sources, with gravitational wave sources in the early universe. Of course, you need full nonlinear gravity in order to study this, and there were also a bunch of things over the past 10 years, I'd say. And then collapse. Like I said before, many people are working on this, either within the scalar field paradigm or with collisionless particles. There was a paper a few days ago by this group, PI by Chulmun Yu, who put out a paper about spindle collapse in numerical relativity, but they're by far not the only ones that do this. Again, like I said, at this point there are many things that you can simply download and use for doing numerical relativity. The one that I use, and I think it's a bit of the standard in open source numerical relativity, is called the Einstein Toolkit. You can go to this website and get instructions how to download it and run it. It's got very many modules that do different things. Most of them, as you can imagine, are dedicated to gravitational wave sources. Some of them are sort of meta code that helps you run your code on different systems, support your code, and supercomputers. So many of us tend to run on a lot of different supercomputers worldwide, and so porting your code is an important aspect, and that essentially is done automatically within the Einstein Toolkit. And there's a lot of material for new users as well that helps. What is in the toolkit that is relevant to cosmology is essentially first the integration of Einstein's equation, and what is called the BCM formalism. It's a particular way to decompose your equations that's, let's say, conducive to numerical integration. There's various ways in which you can construct observables in a gravitational simulations, various utilities to do visualization of your data, etc. And for a couple of years, I've been putting in parts that are important for cosmology. So until maybe not so long ago, there wasn't something that could solve for initial data. Those famous four equations that were the first one that I've shown, part of the projection of Einstein's equation. And you can take a look at this. So there's a code. This is now also in the toolkit. So that part is taken care of. There's a dust evolution code that was described last month in a paper. So you could do evolution of inhomogeneous dust cosmologies. there's various analysis modules that you can use, for instance, to measure back reaction. And then as of this morning, there's a ray tracing module that you can take a look at here. And that also helps because, of course, ray tracing is integral to cosmology, much more, if I want to say, than in the study of gravitational wave sources. And these first three are actually pretty neat because they take advantage of a tool that is called Crank that automatically generates code for you. So you can start from your equation in, say, a mathematical notebook, and you can automatically generate the code that gets plugged into the Einstein toolkit in order to do these simulations, so basically integrate the equations that you want. And we know that the equations for GR, but even for modified gravity even more, can get arbitrarily complex. So this has really been an important tool having in there, in order to guarantee that that the equations are correct, basically. Okay. So at this point, then, based on all these tools, we have to decide what road we're going to take. And in order to construct, say, the first examples of inhomogeneous universes, you can essentially go down two roads. The first one is you try and build what I would define as a relativistic method. You try and find a way to build a space-time that is constituted of discrete objects in full relativity. Kind of like the equivalent, the relativistic equivalent of n-body simulations. And it's kind of like a bottom-up approach. So you take a fundamental building block, the solution for a point mass in relativity, and you try to find a way to assemble all these building blocks into a space-time that is globally a cosmology, basically, and some scale of homogeneity from one scale up, a certain scale. The other one is that you take a model that is homogeneous and then you try to introduce these inhomogeneities in, say, a perturbative way, but then you follow them integrating Einstein's equations, and you could follow them, enter the nonlinear regime and see what happens. And in any case, it all starts with the two constraint equations that I presented before, which in this case, in the case that we use for numerical integration, take this form. This is a slightly modified form with respect to the one that I presented before, again, mostly for numerical purposes. But this equation is essentially the same. You recognize a scalar equation in this psi, which is the conformal factor of the spatial metric, and then you decompose the first derivative of the spatial metric called the extrinsic curvature in its trace, plus this traceless part, and this also gets its equation. So in order to have initial data that then are physical, that correspond to a solution of Einstein's equation, then they need to satisfy these two equations. And of course, so again, I said these are two PDEs. In principle, there are methods for it, but and again, we could sort of mimic what people do in for say binary neutron star, binary black holes, and try to find a solution. But we are in a significantly different setting because these problems are now have to apply to periodic spaces. So people who do, say, binary black holes tend to study asymptotically flat spacetimes, and that's a huge simplification. When you do periodic boundary conditions, you have to be extremely careful about the numerical solution to your equation. First of all, you know, if you try to solve Poisson's equation on a torus, that doesn't really have a solution unless your density integrates to 0. And in relativity, we're a little luckier because Poisson's equations gets extended into an equation that has many terms. So unlike that case, there are some conditions under which you can find solutions. This is described well in this paper. But you have to make sure you are under these conditions. You have to be aware of them. So there's an integrability condition that is going to hold at all times for all the models that I will present in this talk. Notwithstanding this, when you choose the initial data, so we saw that there's basically 4 equations that have to be satisfied. But in principle, you have the whole metric tensor and its first time derivative that you can set as initial data. So those are 20 quantities. So there's many of them that you have to decide what to set to. And of course, much of this is going to be gauged, but there's also physical degrees of freedom in there. And you have to decide what you want to put in the initial data to make it as a sort of realistic, as close to what you want to do as possible. And in a sense, periodic boundaries give you even more freedom, because when you have asymptotic flattening, you know you're basically imposing that your metric, say, goes to Minkowski far away. When you have periodic boundaries, you're just saying that whatever is here has to be equal to whatever is here. And so, in a sense, you have even more freedom, which sometimes means even more problems. And finally, once you've decided what your theoretical approach is, what the prescription for the initial data is, you have to make sure that this blends in well with the existing algorithms, because you can very easily break an algorithm when you start doing something different. So for instance, we said that there has to be an integrability condition in order to find solutions to this equation in periodic spaces. This integrability condition has to be enforced during the solution process. And so you, in a sense, you have a doubly constrained system. On one side, you have the integrability condition. On the other side, you have the Einstein constraints, those 4 equations that I showed before. And you have to find the intersections. Okay, I hope you didn't care about this. Let's see if I can put it back together. So basically, you have to make sure that both of these 2 things are okay. That both these 2 things are enforced, and you're actually converging to the sort of the intersection of these 2 constraint surfaces. And so all of this, and there's a very nice description of this process here. And so all of this stuff has to be overcome before you can find a solution. So, okay, so basically the first approach that I said, we take fundamental solution to GR and stick them together, is the one that Tim presented yesterday with binary black hole lattices. So you have a solution, which is that on a single black hole. You cut a piece out of it, and you try to find a way in which you can stick together all of these black hole lattices and all of these black holes in order to get a global solution of Einstein's equation. And Lindquist and Wheeler were the ones who started thinking about this in 1957. And essentially what you would get if you were to do this was a space where you have all these regularly spaced singularities in which you could study its cosmology. For instance, you could cut out one of these fundamental cells and follow something like the length, the scaling of a proper length of one of these, and see how this will compare, for instance, to the scale factor in an FLRW cosmology. Okay, so now there's a prescription on how to do this in asymptotically flat spacetimes. But unfortunately, this prescription, if you try to do this, boils down to a series that is, in fact, it's bounded from below by some sort of generalized harmonic series. So you cannot possibly superimpose black holes that you would do in an asymptotically flat spacetime. And this comes down exactly to that integrability condition that I was saying before. If you have a periodic space like this, when you integrate this equation, you have to ensure that one of these terms remains alive. You cannot set all of these terms to 0, otherwise you would have something that is definitely non-zero. The sum of the masses of the black hole equal to 0. That's an equation that's an end solution if you have masses of the black holes. For the technical details, you can take a look at one of the papers on black hole lattices. And so basically what happens is that the very simple prescription stitching together Schwarzschild black holes doesn't work. You have to do something to these other variables. The sort of scalar curvature or the extrinsic curvature have to remain non-zero, or the density if you want to include some other component into your spacetime. And it turns out, in fact, that this condition, this integrability condition, is completely general. It's not something that is unique to black hole lattice. Any periodic solutions to Einstein's equation have to satisfy this. And so if this is the case, so this has been explained both here and here, basically. This is a slightly more physical paper that you can read about this, the fundamental no-go theorem for initial data. And this holds for whichever type of relativistic initial data you want to set up for cosmology. And so one option is that you keep alive this term, so you construct a space which is conformally curved. This has been done in the case of the S3. So if from this equation you notice that R must be positive, S has been positively curved. And alternatively, you can keep alive a term that represents the extrinsic curvature, so the first derivative of the metric. So you start to recognize cosmological things there. Here we have a curved space with zero derivative of time derivative of the metric initially. So this is the moment of, analogous to the moment of recollapse of closed cosmologies. And here you have basically a zero spatial curvature, but non-zero time derivative of the metric initially. This is analogous to open or flat cosmologies. And we can follow the numerical integration of both these cases. So this is, again, something very similar to what you saw in this talk from yesterday. Again, we could take, for instance, the length of one of these cells and follow its evolution in time. We'll find that this remains pretty close to FLRW, to an appropriately fitted FLRW. We can do exactly the same on a flat cosmology, find more or less the same things. And these results were quite puzzling to us when we obtained them, but now we have a lot of this is exactly what I was talking about before, this framework of theoretical indication of why this would be the case. Now, the expansion may well stay close to FLRW, but we could already see some effects of the fitting problem because the masses that we needed in this model in order to get the same expansion rate as an FLRW cosmology was slightly corrected. So we did see an effect, a mass dressing, if you want. And then if you go ahead and do, for instance, light trace, and this is the newest results that I'm going to be presenting today, you realize that, in fact, things start to become very different from a homogeneous cosmology. So you could take a cell of your lattice, a black hole would be in the middle. You could start looking at geodesics that, say, propagating along the edge or along the diagonal of the phase. And you can take a look at the results here, but there's some three main points that we find out, three lessons that we learn from these studies. The first one is that the FLRW cosmology that fitted the length scale doesn't fit the optical properties at all. You're much better off using what is called the empty beam approximation, the one that was proposed by Zeldovich and Sixon and Dyer and Reder. And that actually does a pretty good job. And so there's a significant, and this discrepancy does not change as you make your lattice more and more homogeneous. So you could decrease this compactness parameter of the lattice, things don't change, the differences overall. And finally, if you then come and try to fit this with an FLRW, inserting a fictitious rotation, a fictitious cosmological constant, or a fictitious fluid with a negative pressure, we could actually get an agreement. We get a sort of time-dependent, redshift-dependent lambda, if you want, or W, but we can't do this. And this is also not terribly new. People knew about this. You could make up these models where you fit something that propagates in vacuum with a cosmological constant. But this was really the first, or probably one of the first measurements where this was done in an exact space-time that wasn't back reaction free by definition. And so what we found, basically, these are just pictures to illustrate what I said before. So the geodesic A and geodesic B, so imagine that geodesic A is the one that propagates along the edge, and geodesic B is the one that propagates along the diagonal. And as you can see, the EBA, the empty beam approximation, is the one that fits at least geodesic A the best. And EDA unstandard doesn't do very well at all. Lambda CDM is a little better. Milne also doesn't do very well, and this is the residual to that fit. And so again, here you see that essentially the red curve is the one that works the best. And if you try to do this, again, as I said, to go to the continuum limit, in this sense, if you decrease the compactness parameter, you see that in fact, so these are fixed fixed redshift measurements of the luminosity distance for different lattices. They're more and more homogeneous. And you can see that they converge, in fact, away from EBS. The extrapolated value for mu equal to 0 is this green triangle. And this is the fit that I was talking about before. So if you just take a cosmology, put in a cosmological constant just to see if you can get a curve that matches the data, then this will be the appearance of your omega lambda. And well, there's a number of features here that I don't have the time to go into, but you can take a look at the paper. We can discuss later about this. And Okay, very quickly. So, of course, as I said, here's the code that does inhomogeneous cosmology also with the dust component. You can take a look into this. Mostly what we wanted to see is these black lattices were so odd that we just, and extremely nonlinear, they didn't really have a perturbative limit. And so we really wanted to convince ourselves that things were correct as if you want the perturbation with chin dash 0, so you can't do that with black lattices. And so with Marco Bruni and independently another group, we took a look at this problem by simulating inhomogeneous cosmologies with a dust component. And well, the punchline of this is that you can in fact reproduce the perturbative limit very well. This is represented, for instance, okay, I'm going to skip this, you probably know exactly what I'm talking about. Is that you can see, so here you can construct a model with decreasing density contrast, and you can see that as a matter of fact the numerical relativity simulations stay quite close to the perturbative regime for small delta, and then you can follow the transition to the nonlinear state quite well. And you find different things, and you're able to quantify a number of things such as how the expansion rate will be affected by these inhomogeneities, how collapse happens with respect to certain relativistic models, and you can measure the back reaction, one of those elements that people have to make up basically so far. And unfortunately we can go into this, or the feasibility will have to be discussed offline, but just giving a summary, the first important part, the first important lesson from this is that you can build these models. They, in fact, give you sort of more information than what the perturbative counterparts or Newtonian counterparts will tell you. And to one extent, these are feasible. And the early results that we're getting, so most of the models that are presented are very simplified, but you can already see a number of things. First is initial data knowing theorem has been really important in obtaining the results over the past few years. We have found this, and now we believe we understand, at least at some level, why these models expand exactly like FLRW models. So that's sort of that emergent FLRW behavior that Tim was discussing yesterday. And finally, we've started doing light propagations, and we've started to see what the high order effect of these models are. And these are things that you cannot basically get otherwise. And with this, I will conclude. Thank you.
Thank you, Eloisa, for this illuminating talk. Questions, Timothy?
So it's very interesting to see that your optical properties look like we get affected by radar approximation using this MTB. That seems to be in contradiction then to the expectations that Weinberg had, that Tom Kidlam was followed up on, that the shear should replace the terms that come from the Ricci curvature, focusing at the B.
Well, so keep in mind that we have studied very special curves. So of course the other question is how exactly this would generalize completely. So we're basically studying one curve that propagates along the edge. So many of the, as you know, many of the terms here will basically be zero, and in a sense we think that's the reason why the EVA works so well. The other curve, which was geodesic B, the one that goes along the diagonal, in principle has got shear terms, got bio, but and that means that the agreement with the MTB approximation is worse. And how exactly, whether the Weinberg results will be able to explain this, we haven't quantified, but we suspect that will be the case.
Yeah, so Weinberg's result relies on an average over a sphere, I think, shooting LGD6.
Yeah, so that's the other thing that again makes me suspicious how we can match this by individual GD6. And again, given that this is a vacuum spacetime, it's really hard to think about averages because, of course, you'd have to decide over what class of observers you're averaging, and some observers are going to be completely special here, and you really don't want to put them into a cosmological average. And so this is a problem we thought about for a long time, and in the end we decided not to put it in this work because it's a much longer investigation.
Yes, it's actually related to Tim's comment. I think so about the Weinberg argument. I think one first thing which is worth emphasizing that it is actually wrong. So the Weinberg argument, as stated in the paper, in the original paper, it is wrong. The second thing is that it can be well, you can find things that look like it, but they rely on the fact that you have transparent lenses, which in your case is definitely not the case because you never cross the black holes.
Yeah, exactly.
So you have a strong amplification in those cases. But yeah, I think it's, so I was going to ask again, what are the light rays that you consider? So there are some that are, if you have a picture, maybe I missed that, I think. Okay, that's... Oh yeah, okay. And the black hole is at the center, right?
So we trace many more geodesics in the space-time, but the problem is that it really is hard to separate out what the local effects are from the. So we don't have any guiding principle to understand what to expect of those geodesics. And if you get close to the black holes, at one point you basically just start to get the Schwarzschild geodesics. And in the middle, it's a kind of a gray area. We don't really know what to do. It's much easier to just take a look at things where the effects of the different black holes, in a sense, cancel out. By construction, the local effects are minimal. And then, yeah.
So yeah, shear tends to accumulate actually when you pass by close by the black holes. This is what Tim and Pedro have seen in their paper, and Julien and Jean-Philippe Bouton as well. So I think you would see the same kind of effect if you have some random lines of sight that that come close to the black holes. You see shear starting to make the thing deviate from the intervening observation.
Last question.
Coming back to your 2 Hertz variable Q, right? That was for gas cosmologists.
That's right.
How feasible, is it difficult, impossible would be to generalize it for other kind of equation of state, trying to incorporate gravity beyond GR, let's say. The equation of state not for dust, but for something effective.
Okay, so that depends on the equation of state, and that depends on the theory of gravity. So I assume that some generalization of some extensions to GR will be relatively simple. Others are probably really hard. It depends on in a sense, the numerical, the character of the equations. If it's something that resembles, let's say that the principal part more or less looks like GR, then probably it's not too bad. Again, with automatic code generation, it's perhaps quite easy to just make an experiment, see how it goes. Similar for equation of state, depends on the solvers that you have, whether you're expecting to form shocks, so people who do relativistic hydrodynamics for neutron stars have a very sophisticated infrastructure that lets them, for instance, handle shocks correctly. And in a sense, that was the simplest possible thing that we could do, and we didn't need a lot of infrastructure. If you change that, probably. So from the theoretical standpoint, I think it's no problem. From the numerical standpoint, it can be a lot of.
Do you rely on the integrability condition? Do you rely both Q and the other variable, the variable?
No, okay, so first of all, we really only use the integrability condition to make sure we get initial data. So we don't keep looking at it over the evolution. There's reasons why we believe it's preserved.
Because it's not beyond GR. As soon as you take all the theories, you don't have a zero.
Yeah, exactly. So. Yeah, exactly. So I don't know how constraints will work. It depends on the theory.
Okay. Thank you. Let's thank Eloisa again.